Find a link to the article in the description box below.
Robust acceleration of Earth system heating observed over the past 6 decades. Abstract. Global heating of the Earth system is unequivocal. However, detecting an acceleration of Earth heating has remained elusive to date, despite suggestive evidence of a potential increase in heating rates. In this study, we demonstrate that since 1960, the warming of the world ocean has accelerated at a relatively consistent pace of 0.15 plus or minus 0.05 W/m2/decade, while the land, cryosphere, and atmosphere have exhibited an accelerated pace of 0.013 plus or minus 0.003 W/m2/decade. This has led to a substantial increase in ocean warming, with a magnitude of 0.91 plus or minus 0.80 W/m2 between the decades 1960 to 1970 and 2010 to 2020, which overly substantial decadal scale variability in ocean warming of up to 0.6 W/m2. Our findings withstand a wide range of sensitivity analyses and are consistent across different observation-based data sets. The long-term acceleration of Earth warming aligns qualitatively with the rise in CO2 concentrations and the decline in aerosol concentration during the same period, but further investigations are necessary to properly attribute these changes. Similar content being viewed by others. Identifying a human signal in the North Atlantic warming hole. Warming trends increasingly dominate global ocean. Globally resolved surface temperatures since the last glacial maximum. Introduction. In the past 150 years, Earth's climate has been warming at a rate that is unprecedented in at least the last 2,000 years. This human-caused warming has caused widespread adverse impacts and related losses and damages to nature and people, which will continue in the future as global climate continues to warm too. Detecting changes in the rate of warming is crucial for informed decision-making in international climate negotiations, with the aim of limiting global warming to specific levels. However, it remains a significant challenge to detect such changes due to the substantial internal variability of the climate system on a decadal scale, example Ref 3. In this paper, we address this challenge by examining the global heat accumulation rate across the entire climate system, including the ocean, atmosphere, cryosphere, and land. By focusing on this integrated view, rather than solely relying on changes in global mean surface temperature, we can mitigate the impact of variability and gain a more comprehensive understanding. 4,5. Global heat accumulation in the climate system, resulting from the current positive Earth's energy imbalance, EEI, at the top of the atmosphere, is primarily dominated by changes in global ocean heat content, GOHC. 4. GOHC changes account for approximately 90% of the total heat increase in the past 50 years, while land heating, ice melting, and atmospheric warming contribute around 5%, 3%, and 1% respectively. 6,7,8. Several studies have indicated an increase in the global heat accumulation rate in recent decades, with values rising from 0.50 0.32 to 0.69 W/m2 during the period 1971 to 2006 to 0.79 0.52 to 1.06 W/m2, 90% confidence interval, for the period 2006 to 2018. Ref. 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22 and Fig. 1. Some studies have even suggested a potential doubling of EEI in the last decade compared to the previous one. 6,17. Assessment of observation-based Earth's energy imbalance, EEI. Absolute values as available in the literature, considering various approaches and time periods, refer to Table S1 for references. The black circles highlight the EEI values derived from an international assessment conducted within the Global Climate Observing System 7, GCOS, framework. Notably, These values show a significant agreement with the EEI values estimated in the latest IPCC Report 4, which are represented by the purple circles. Despite this suggestive body of evidence, no study has conducted an analysis of heat accumulation acceleration since 1960 to date. While the results presented in Fig. 1 provide insights, they represent accumulation rates computed over varying time spans, with higher rates calculated over decadal periods and lower rates calculated over multi-decadal periods. This variation in time spans makes it challenging to make definitive and quantified statements about acceleration. Additionally, the use of diverse datasets and methodologies can significantly impact the calculated accumulation rates. The only notable climate variable where acceleration has previously been detected in past decades is global mean sea level, GMSL, 23, 24, 25, 26, 27, 28, 29, 30, 31. This GMSL acceleration has been attributed to factors such as increasing GOHC leading to thermal expansion of seawater, declining land water storage, or increasing land ice melt 25, 26, 27, 31, 32. In this paper, we present the first observation-based quantification of the acceleration of Earth system heating. Our study adopts a systematic approach, incorporating multiple datasets and employing various methods. We estimate the rate of change and acceleration of Earth's heat content using a collection of GOHC time series derived from in situ temperature data spanning from 1960 to 2020. Additionally, we utilize ocean reanalysis data from 2005 to 2020 and satellite altimetry and gravimetry data from 2002 to 2020. To complement our analysis, we also incorporate non-ocean heat content time series covering the period from 1960 to 2020, and compare our findings to observations of the net radiative flux at the top of the atmosphere, TOA, spanning from 2001 to 2020. Heat content rate of change. Several research groups have developed four-dimensional global ocean temperature data sets, which enable the estimation of GOHC. In this study, we use an ensemble of 10 freely accessible products, refer to Table S2 for the exhaustive list and associated references, and take a systematic approach to assess their consistency and discrepancies, see Methods section. We compare this ensemble mean to three other estimates of GOHC based on the ensemble mean of 3 ocean reanalyses, 1 satellite-derived estimate 20, and a composite ensemble 7 of 16 products developed within the framework of the Global Climate Observing System, referred to as GCOS heat content. It should be noted that not all products cover the same time period, see Fig. S1 and Table S2, and we have aimed to maximize the number of products used for each discussed time period throughout this paper. None of these GOHC estimates can be considered flawless. The process of producing these estimates is accompanied by significant challenges stemming from observational gaps, historical changes in observational coverage, and potential sensor errors 33, 34, 35. Consequently, each research group must make important assumptions regarding data quality control, data correction, and strategies for filling spatiotemporal gaps. These assumptions collectively contribute to the uncertainty associated with the reconstruction of the GOHC 36, 37, 38. Unfortunately, producers do not always provide the GOHC uncertainty associated with their methodological choices.